Have you ever walked into a supermarket with hundreds of items placed randomly on the shelves? Imagine trying to find your favorite snack, total chaos, right? That's exactly how early chemists felt in the 1800s. By that time, around 31 elements were known. But as new elements kept being discovered, 63 by 1865 and over 114 today, the study of individual elements and their compounds became overwhelming. With every new discovery, it became more and more difficult to store and apply chemical knowledge efficiently. Scientists urgently needed a system, a way to group similar elements together, to make predictions, and to streamline learning. That's how the journey toward classifying elements began, not just to tidy up the known world, but to uncover the unknown as well. And just like that, chemistry began building its own version of a supermarket, the periodic table. The first attempt at bringing order to the element chaos came from Johann Dobryna in the early 1800s. He introduced the idea of triads, groups of three elements that showed a curious pattern. For example, take lithium, sodium, and potassium. Lithium has an atomic weight of 7, potassium has 39, and right in between sits sodium with 23, nearly the average of the other two. Not only that, their properties, such as reactivity and appearance, also followed a trend, with sodium showing intermediate behavior. This was called the law of triads. But despite its novelty, the model was short-lived. Why? Because it only worked for a few element groups. The scientific world dismissed it as a coincidence, but Dobryna had sparked something big, the first glimmer of periodicity in properties. Fast forward to 1865, another chemist, John Newlands, proposed a musical twist to classification. He arranged known elements in the order of increasing atomic weight and observed something fascinating. Every eighth element had similar properties to the first, much like musical octaves where notes repeat. For example, sodium and lithium, both reactive metals, stood 8 places apart. This was called Newlands' law of octaves. Although brilliant, it stumbled when applied beyond calcium. The heavier elements didn't obey this 8-note pattern. The scientific community was skeptical, but they couldn't deny the potential of a recurring pattern in elemental properties. Despite initial rejection, Newlands was later honored for his work, which turned out to be a stepping stone toward a much greater discovery. Then came a major breakthrough. Dmitry Mendeleev, the Russian chemist often credited as the father of the periodic table. In 1869, Mendeleev arranged elements by increasing atomic weights, just like others before him. But his genius lay in the vertical grouping. He placed elements with similar properties in the same columns. His periodic law stated, the properties of elements are a periodic function of their atomic weights. What truly set Mendeleev apart was his boldness. He left intentional gaps in his table for elements that hadn't yet been discovered, like eka-aluminium and eka-silicon. Even more impressive, he predicted their properties. Years later, when gallium and germanium were discovered, their actual behavior matched Mendeleev's predictions closely. For instance, he predicted eka-aluminium would have an atomic weight of 68 and form the oxide E2O3, and gallium, with atomic weight 70 and oxide G8O3, fit perfectly. Mendeleev didn't just organize the known, he forecasted the unknown. Despite its brilliance, Mendeleev's table wasn't without flaws. Some elements didn't quite fit if atomic weight alone was followed strictly. Take iodine and tellurium. Iodine has a lower atomic weight, but Mendeleev placed it after tellurium because it shares properties with chlorine and bromine. He trusted chemical behavior more than calculated mass, a bold move for that time. Moreover, without knowledge of subatomic particles, he couldn't explain why these periodic patterns existed in the first place. But still, his strategy of leaving gaps and trusting chemistry over numbers became the foundation for what would eventually evolve into the modern periodic law. Meanwhile, in Germany, Lothar Meyer was independently developing similar ideas. Around 1868, he plotted graphs of atomic volume and other properties against atomic weights and noticed repeating waves, clear evidence of periodic trends. However, his work was published just after Mendeleev's and didn't gain the same level of attention. Meyer's version of the periodic table was surprisingly close to our modern form, and his scientific contributions supported the idea that elemental properties vary in a regular, periodic fashion. While Mendeleev rightly takes center stage for prediction and table building, Lothar Meyer's role in quantifying the periodicity was equally vital. So, let's look back on the journey we've just taken. From Dobrynin's simple triads to Newland's musical octaves, and finally to Mendeleev's bold periodic law, the classification of elements evolved step by step. Each attempt reflected a growing awareness that element properties are not random but follow patterns. Mendeleev's predictions were spot on not by luck, but because he tapped into the deeper order of nature. And while his method was based on atomic weight, the scientific world would soon discover that it was the atomic number, the number of protons, that truly governs periodicity. The genesis of periodic classification wasn't just about making tables, it was about seeing chemistry as a unified story guided by nature's invisible logic. I hope this session helped you see how the periodic table, that colorful chart on your classroom wall, is not just a tool, but a historical triumph of scientific reasoning. Catch you in the next class, where we uncover how the modern periodic law emerged from atomic discoveries.